This webcast talks about displacement and distance, and then we'll talk about the difference between velocity and speed. In worksheet 2B, the fifth question gives us an overhead snapshot of Dorothy walking her puppy Toto. And you can probably relate to this. I know when I walk my dog, I tend to stay on the sidewalk, and so I walk in kind of a straight path. But my dog, and I like to use those long leads that are retractable, and she'll go, she searches down the rabbit trails and sniffs them down, or she'll go over here to sniff at something or a place to use the bathroom. So she tends to move many more steps than me off the path, and that's what we're seeing here. The solid line shows Dorothy's path, and the dashed line shows the puppy Toto's path. And the question is, if you look at it from start to finish, who traveled further? Now, at first glance, I'm thinking Toto did, because I'm looking at this dashed path that Toto took, and if I could imagine straightening that dashed line out, into just a straight line, I think that dashed line would be longer than the path that Dorothy has walked. But, as I look at it a little bit more deeply, if I compare the starting and ending points of both Dorothy and Toto, I see that something strange, is happening here. Look, Dorothy's final position is further away from her initial position than Toto's final position is from where he started. So if you just cared about who actually managed to reach a further point from where they started, then you might say that Dorothy has traveled further. So there are really two ways of looking at who traveled further, and I think they're both valid. If we talk about who ended up traveling further from their starting position, well, Dorothy did that. So Dorothy has the larger displacement from where she started. But if you want to talk about which one of these people actually traveled a longer path length or took more steps, well, I think Toto did that. He had the longer path length because, he took more steps. He was zigzagging in and out. So Toto has the larger distance. And so in physics, we want to have clear definitions for both of these things, displacement and distance, because they really are different ways of looking at this question of how far. So let's look at the definitions for each one. Displacement is represented by the symbol delta x, and it is always calculated as the final position minus the initial position. Displacement is the shortest straight line distance between the initial position and final position. It does not depend at all on the path that the object takes to travel between initial and final position. It only depends on where the object started and where it ended up. Now, displacement is a vector quantity. That means that displacement is giving us two types of information. The amount of the displacement, which is called the magnitude, well, that tells us how far. And the sign, which means positive or negative, the sign of the displacement identifies what direction the object moves. So an object that has a displacement of 2 meters moved 2 meters in the positive direction. But an object that has a displacement of negative 2 meters moved 2 meters in the negative direction. So the sign is giving us important information. Now, distance, which is also called path length, they're used interchangeably. Distance is represented by the symbol d, that's a lowercase d. I bet this formula looks complicated to you, and I hope to show you in the next example that it's not too bad. But to find the distance, we have to take the sum of the individual displacements of each part of the trip. And actually, we're adding up the absolute value of the individual displacements. So in this formula, the sigma sign, that's the thing that kind of looks like the backwards z, is saying take the sum of all these things. And then the things that we're taking the sum of are the absolute values of the displacements. Now, distance is the total path length that the object travels as it goes from the initial position to the final position. We want to count every step, and we are disregarding direction. We take every step as if it's in the positive direction. So if you could imagine a flexible tape measure or string or something that's being laid down as the object moves around, and then after they're finished moving, you could straighten that out into a straight line and then measure the length of that tape measure. That would give you what we mean by distance or path length. Distance is a scalar quantity. It is not a vector. It has no information about the direction that the object moves. It's always a positive quantity. Distance is always positive. Let's look at a simple example to try to understand the difference between these two things. So my example is a dancer doing some type of dance routine. And first she takes 2 steps in the positive direction, and then she takes 5 steps in the negative direction, and then 2 more steps in the positive direction. And I'm just assuming that each step is a meter long, just for simplicity. So I've kind of put a diagram here to help me understand how this dancer is moving, and I assume she started at 0 meters. So she takes 2 steps in the positive direction first, so she goes from 0 meters to 2 meters. Then she takes 5 steps back in the negative direction. That takes her to a position of -3 meters, and then she takes 2 more steps in the positive direction. So she ends up at a position of -1 meters. Okay. Now to find her displacement, the delta x, I take the final position minus the initial position. Well, her final position was -1 meters, and her initial position was 0. She started at 0 meters. So her displacement was -1 meters. We know now that during the course of this dance routine, the dancer was displaced 1 meter in the negative direction. Well, what was the distance that the dancer traveled? To find the distance, I have to add up the absolute values of the individual displacements. And I mean for each portion of the trip. So in the first portion, she moved in the positive direction, 2 meters, right? That displacement was final minus initial, 2 meters minus 0 meters. That was 2 meters. In the second part of this dance routine, she took 5 steps in the negative direction. Those 5 steps, the displacement would be found as her final minus initial position. Well, in that middle part, her final position was -3 meters, and her initial position was 2 meters. The absolute value of -3 minus 2 is 5, right? She moved a distance of 5 meters when she took 5 steps in the negative direction. And then I also have to add the absolute value of the displacement for the third part of the trip. So in the third part of the trip, the displacement was from an initial position of -3 meters to a final position of -1. So displacement is final minus initial, -1 minus -3. That's a displacement of 2 meters. Okay, I add those 3 portions of the trip together, and I figure out that this dancer traveled a total distance of 9 meters during this dance routine. So we now understand the difference between displacement and distance. Those are talking about how far something goes. Now let's talk about 2 ways of talking about how fast something moves. So one of them is velocity, and velocity equals the total displacement divided by the elapsed time. Velocity is a vector quantity. It has both a magnitude and a direction. Notice you're calculating velocity with displacement, which is also a vector quantity. So the magnitude, or the amount of the velocity, that's the speed of the object. Okay, so that's what we commonly talk about when we talk about how fast something's going. The sign of the velocity, whether it's positive or negative, is identifying the direction of motion of the object. So be careful, because since velocity is calculated using displacement, sometimes this can lead to some surprising results. So let's think of an example, very simple, of Eleanor, who is running around a track. And she starts at a position, and she ends up at exactly that same position. So her displacement is 0, right? Final minus initial position, well, they're the same number. So her displacement was 0. She's back where she started. So a physicist would say that her average velocity is 0 because her displacement is 0. Then let's talk about speed, which is another way of talking about how fast something moves. Speed equals the distance, or the path length, that the object moved divided by the elapsed time. Speed is a scalar quantity. It doesn't provide us any information about the direction of motion. Right? We are using another scalar quantity, distance, to calculate the speed. So speed is always a positive quantity. By the way, there's no symbol for speed. We just write speed when we're calculating that. Okay, and then I wanted to show one final example, because sometimes we talk about a trip where there was one velocity for the first part of the trip, and then the velocity changes. And so I just wanted to caution you that you cannot average velocities. In order to find the average velocity, you need to find the total displacement and then divide by the total elapsed time for the trip. And I have an example here, which I'll show here in this yellow box. So this is a trip in 2 parts. For the first 8 seconds, the velocity of the object was 2 meters per second. For the last 4 seconds, the velocity was 6 meters per second. So if we wanted to know the average velocity for this entire trip, we cannot add the 2 plus the 6 and divide by 2. That would give us 4 meters per second, and that's not actually the average velocity of this object. Instead, we have to find the total displacement and divide by the elapsed time for the whole trip. So I can see that this object starts at a position 0 and ends at a position of 40 meters. So the total displacement was 40 meters in the positive direction. The total time was 12 seconds. So here, the average velocity of this entire trip was 3.33 meters per second. If we wanted to show that graphically, that would be like drawing a line from the initial position to the final position and then finding the slope of that line. This slope of the line between initial position and final position, that is the average velocity for the entire trip.